Foam tolerance controls the shape of the part feature. There are 4 types of foam tolerance. The first one, straightness, fatness, roundness, and the last one, centricity. Of that, foam tolerance do not require datum. First foam tolerance is straightness tolerance. Straightness tolerance can be divided to surface straightness and axial straightness. Let's have a look on the sharp example first. Surface straightness is actually the 2D versions of the fatness tolerance. So from drawing, you can see that the arrow of the control frame is actually pointing to the surface of the shot. What does this mean? So let's have a look on the tolerance zones. Here is the part of our study. The feature control frame is actually pointing on the top surface of the shot. So this is the tolerance zones. As you can see, this is the 0.1 tolerance zone. As long as the surface of the shot lies between these two planes, 0.1 plane, like the yellow color curve, so the tolerance can be fulfilled and is considered within the limit. Unlike surface straightness as the 2-dimensional tolerance, axial straightness actually is the 3-dimensional tolerance. From the drawing, you can see that the feature control frame is actually applied to the dimension, which is the diameter of the shot. It is not applied to the surface like surface straightness. It means that it controls the axials of the shaft instead of the surface. Let's have a look on the tolerance zone. As long as the control frame is attached to the dimension, so it will control the axials of the shaft instead of the surface. So this is the axials of the shaft. And here, this is the tolerance zone with a diameter of 0.1. As long as the axials is lies between this tolerance zone, so it is within the spec. Just a representations of the axials in yellow color curve. For axial straightness, the modifier can also be added to the feature control frame. So it means that in maximum material condition MMC, when the diameter is 3.1, the straightness should be controlled in 0.1. So it means that with MMC, we're able to get a bonus tolerance when the diameter is actually smaller than MMC. This MMC application particularly useful when we want to make sure that the shaft can be inserted to the hole. So by considering the maximum visual size of the shaft, then we can make the hole gauge based on the maximum visual conditions. So with this, we can guarantee that the shaft can be inserted to the hole. Moving on to another example, that's a rectangular bar. There are also 2 types of straightness, surface straightness and center plane straightness. For the surface straightness, you can see that the pointer is pointed on the upper surface. But this is the 2-dimensional tolerance, same as the previous example. So this is not applied to the whole surface, but instead is only applied to the extracted line. Let's have a look on the tolerance zone, how it can be interpreted. From the drawing, the pointer of straightness tolerance is applied on any extracted line on the upper surface. In one cross-section, the tolerance zone should be limited by two straight lines in a distance of 0.1. As long as the yellow part surface line lies between these two parallel lines in a distance of 0.1, then this is within the limit. Same also apply to others cross-section. So for other cross-section, the yellow line also need to be limited by the tolerance zones of 0.1. During a measurement, we may measure a few cross-sections. The center plane straightness of the bar is very similar to the axial straightness of the shaft. Same as the axial straightness of the shaft, so the feature control frame is attached to the dimension. So it means that it's not used to control the upper surface, but is used to control the bar axis. So let's have a look on the tolerance zone. When the control frame is attached to the dimension, the tolerance zone will be limited by two parallel planes in the distance of 0.1. As long as the yellow bar axis is lie between these two parallel planes, then this is within the spec. The modifier can also be added to the control frame. So as you can see, the MMC is added here. So with MMC, bonus tolerance can be acquired when the part width is less than 1.2. We all know that the size tolerance can control the foam tolerance. In this example, the bar has the thickness of 1 mm with a tolerance of plus minus 0.05. So the lower limit is 0.95 and the upper limit is 1.05 with a total tolerance zones of 0.1. So why we still need GDT? Because in certain cases, what we concern is on the straightness of the top surface. That's the green surface. But we're not really concerned about the thickness tolerance of 0.05. Let's cross-cut the bar in this cross-section. The straightness tolerance 0.1 is called at the top edges. This yellow line is the tolerance zones with a distance of 0.1. As long as the section line lies between the tolerance zones along the length of the bar, so this is within the limit. Now, we no need to depend on the size tolerance to control the foam tolerance. In fact, we can loosen the tolerance of the thickness to 0.2 or even 0.5. So with the straightness tolerance being called out in the drawing, we can loosen the size tolerance, and this will save some of the manufacturing costs. So the same reason why we need to use GDT is also applicable to the fatness. Next, let's move to the second foam tolerance, fatness. Fatness tolerance is the 3D versions of straightness tolerance. Straightness is related to the variations of a line, while fatness is used to control over a surface. There are two types of fatness. surface fatness and also the center plane fatness. We also call it as the derived medium plane fatness. So for surface fatness, similar to straightness, you can see that the leader arrow is pointing on the top surface. So it means that it will control the tolerance zones on the top surface. Let's have a look on the tolerance zone. Magenta color is the surface we want to control the fatness. Let's have a look on the tolerance zone. So this is the tolerance zones with a distance of 0.1 mm. So as long as the yellow top surface is limited within this tolerance zone, so this is within the spec. Fatness tolerance is usually applied on the surface when we want to have a small variations of fatness. So usually we not really care about the size tolerance. We just want to have a fat surface for some application like jig and feature. Also, it is common to apply the fatness tolerance on the datum. So particularly the Z direction datum, usually we call it datum A. Datum A is a critical functional surface. So by adding the fatness tolerance on datum A, it will help to create a stable surface for manufacturing as well as the consistency for repeatable measurements. After explaining on the surface fatness, let's have a move to the center plane fatness. We also call it as the derived medium plane fatness. Just like straightness tolerance, the tolerance can be applied to the top surface, but it also can be applied to the feature of size. You can see that the feature control frame is actually applied to the dimension of 15. It means that right now it's no longer applied to the surface, but it is applied to the derived medium plane. Let's have a look on the tolerance zone. Here is the model of study. The fatness tolerance will be applied on this derived medium plane. If this plane deviated or warped too much, then it will be out of spec. Let's have a look on the tolerance zone in this plane. You can now see that if the yellow color's surface is lie between the tolerance zones with a distance apart of 0.1, then it is within the limit. For measurement, you can put down your plot on the top surface at this point, then shift down to the opposite side of the bottom surface. We can repeat the process all over the surface until we determine the derived medium plane. Until then, we can check if this center plane can lie between the tolerances of 0.1. Center plane fatness can be utilized on regardless feature of size. It can also be applied to the maximum material condition and less material conditions. In this example, you can see that the modifier of MMC is added to the feature control frame. By using the functional gauge to accommodate the maximum virtual size, we can take the both MMC of the part and also the deviation on the center plate fatness into consideration. In MMC, when the part size is 15.2, the fatness tolerance is 0.1. When the part becomes smaller, 15.1, 15, or LMC 14.8, we gain the bonus tolerance up to maximum 0.4 mm. Here we learn about fatness tolerance. Sometimes it's quite confusing when we want to compare fatness with parallelism and profile tolerance. Here the joint entry for all three tolerance. For fatness, it's fine as long as the surface is lie between the tolerance zones of 0.1. How about for parallelism and profile tolerance? It actually look quite similar, but in fact, they are slightly different. Let's just first compare fatness versus parallelism. The most obvious difference we see is the datum. For fatness, we do not need any datum, whereas for parallelism, it can be oriented by the datum. Fatness is form tolerance, which we only care about the shape of the surface. Whereas for parallelism, it is orientation tolerance like perpendicularity and angularity. All of that orientations tolerance need to be oriented to specified datum. Let's look at another set of joint entry. Now the slope is at on the top surface. For fatness, it's fine as long as the part surface lie between the tolerance zone. For parallelism, the actual surface must be oriented to the datum A. Let's look into more detail. For fatness, as long as the valid and the peak is limited between the tolerance zone, then it's fine. It's no need oriented to any datum, since fatness do not need any datum. Whereas for parallelism, you can see that the dimensioning of the tolerance zone is perpendicular to the datum A. How about the comparison between fatness and profile tolerance? The main difference is profile tolerance can be applied to curved surface other than flat surface. Secondly, profile tolerance can be controlled by datum. When profile tolerance is controlled by datum, it becomes parallelism, where the orientation becomes essential right now. In this case, just remember to put in the datum in the feature control frame. Now we have covered two form tolerance, straightness and flatness. In next video, we will talk about roundness and symmetricity. Thanks for watching. See you in next video.